So welcome to this pre-recording of lecture 42 already of the course Introduction to Symbolic Computation. And this is the last pre-recording, also the last lecture, and the fourth review for the final exam, also counting the two reviews for the midterm exam and the previous review. So the final is scheduled for Friday, 5th August, starting at noon. It will happen online and you will have to submit your answers before 1:40 p.m. So I will go again over the protocol for this exam and then what the focus is of this review, namely of the second half of the course, where we looked into functions, differentiating them, integrating them, and approximating them with power series. And then we had the plotting and the solving of the equations, not only polynomial equations but also differential equations, and we considered polyhedral optimization problems. So in this online course, the asynchronous participation is enabled, but there is one single most event that everybody has to do at the same time, and that is the final exam. So in order to coordinate this, I request that you sign up. So this review is scheduled for Wednesday at noon, so you have 24 hours to sign up to commit to the exam. The exam will have multiple versions, so this is for me to make the exam not too long and still cover the topics that we have seen in this course. One important aspect that we learned in this course was to get familiar with the Jupyter notebook. So your answer must be submitted in one single Jupyter notebook, and you must upload it before 1:40 on Friday, 5 August. Okay, what is the focus for this review? So the review will be comprehensive, we'll cover everything, but what we do with the reviews is kind of shine a spotlight on the most important problems. Now, look at the problems and look at the review also for the second midterm exam. So the second midterm exam has a notebook posted with answers in there. Even if you took the second midterm exam, there were two versions. Also look at the other version, and in particular it would be good if you first looked at the questions before you looked at the answers, and in that way that gives you somewhere guidance on where to study. Some problems might look very easy for you, other ones not. In those cases, please look at the relevant lecture notes. Look at the answers of the quizzes, review the homework problems, and above all, make sure that you understand your mistakes and kind of try to arm you against making the same mistakes. So calculus was the title of the third chapter in our lecture notes. We look into functions. Sometimes you have to use Python functions, and we will see a case of that. Sometimes you better use a Sage math function, but in any case, all functions are evaluated within the context of Sage math. Recursion is a very important problem-solving technique, but it can go really wrong if you make an exponential number of function calls. In cases where the storage is only linear, then memoization will make recursion extremely efficient, and at the same time you get to keep the original definition of the recursive relation. The review problems will start with a function to compute an expression. One problem that we considered many times, and I will have a notebook waiting, I will show it also here now, is the slope of the tangent line at a point on a curve. And you can do this in both ways. I will illustrate both ways. We can also define functions that compute numerical approximations of integrals. Be aware that the fundamental theorem of calculus comes with conditions. And in particular, that means that the function should be everywhere well defined over the integration interval. We have already covered symbolic numeric factorization, so we ended the calculus chapter with this. Very well-known calculus problem is to solve constraint optimization problems. I will focus on one of these problems. On the second midterm, we had the problem of computing the closest point to a surface, and that can be solved with the Lagrange multiplier technique, but that didn't go very well at the midterm. So I will solve this problem. Okay, so then there is the plotting and the solving of equations. So linear equations, polynomial equations, differential equations, and then polyhedral and unconstrained optimization. As far as the plotting is concerned, I will give an example for the questions how to convert to polar coordinates. But also note that we have seen three-dimensional curves. So these are space curves which can be defined by the intersection of two surfaces or parametrically. So on the midterm exam, second midterm exam, there was a question there. And do not assume automatically when you see the word curve that it is in the plane. So if you see three variables, if you see equations in three variables, then you know you have to deal with space curves. So not everything what is in three variables is a space curve. If you have one equation in three variables, then it defines a surface. So in three dimensions, we have extra complications that the objects that we compute or that we plot are different, have different dimensions. Okay, so that is an overview of the problems that we considered in the second part of the course. So you also see here animations in there, and after the second midterm we did interact. That was covered by the computer project. Okay, so let me now transition from the slides into the Jupyter notebook. So the Jupyter notebook is a Sage Math 3.9 kernel. I'm very well aware that there are some differences between the versions, and by default I will grade your exam with version 9.6, and I have tested my Jupyter notebooks also for other versions, for the most recent version. Okay, so let me discuss the first problem. The first problem is the definition of a function which computes expressions. So we want to define polynomials. We want to define a system of polynomials. Here you see the general formula that is working for n variables, and the outer index the outer index is k, runs from 1 to n. So here you see the kth polynomial, which starts with the kth symbol in a list of symbols. So if you want to do this piece by piece, you would look only at one term. And you would actually start, so you have to test your function on 8 variables. So here you see the start. So the start of every question is a reset. So I would recommend you to do so. In this way, you can solve the problems in any order on the exam. You always start with a reset. So in this way, you don't get any baggage from other previous questions that you solved in your notebook. So how does this begin? Well, you begin with defining a list of variables. Here in the question formulation, we start at 1. So also the k then ranges from 1 to 8, knowing again with Python that we end at the last index minus 1. And you see the construction where I'm using the addition here of two strings and the percent operation to generate the numbers. The numbers which are the indices to the variables. And then the solution is actually a one-liner. So here this is a case where you must use Python function to prevent the premature evaluation of the selection of the variable. If you were to use a SageMath function for this, you would get into trouble with the index of x. Now note that the first variable is called x1. However, it appears at place 0. So that's why you see here the k minus 1. Here is the k minus 1. Okay, so then the index I here ranges from 0 to n minus k minus 1. So here I'm exploiting the fact that I'm now working with I going from 0 to n minus k minus 1. This is expressed here with n minus k. So you can see that this corresponds to the indexing. Note that there is a difference between the little x, which is the representation of the letter that is used for the variables, and the capital X, which is the list that stores all the variable names. Okay, so, and then we test this for 8 variables. I'm running a list comprehension, and here you see the polynomial system that is defined by this function. Okay, so you can see if you had done this piece by piece and left the sum out, you would have the x1, x2, x3, x4, x5, x6, x7, x8, which is now at the very end, because it's the lowest degree monomial. Okay, that's the first question. The second question is a little bit more involved because I wanted to fuse two topics together. So this is very good for a review. But this is an integration problem where you may have to assume facts about the upper limit of the integral. So you see that the integral goes from -1 to b. Now if the b is positive, then you have a problem for x equals 0. So you can already see that there are problems with evaluating that integral. Now this is a fused question in the sense that this is a nice application for a piecewise. So with a piecewise, one can define, and actually it will be possible to define one function which gives the correct answer for all values of b. So this is a function of b, the upper limit in this integral. Okay, how do you begin on this? Well, first solve the integral question. So I define the integral, and you can do this the straightforward way, but here I did it a little bit more subtle. We saw that we could um, prevent the evaluation. So this is useful for the numerical integration, but also very useful if you just want to check whether the problem is defined correctly. Okay, so we will evaluate this integral within a context. So if you evaluate this without assumptions, then the integrator will actually prompt you. So in some sense, I'm giving you here the clean, nice answer. At this point in time, you must have already received many error messages from SageMath, which might be rather intimidating at first, but here in this case, if you have the stomach to read, and at this point in time you shouldn't be scared anymore of this, the error message is actually very useful. It actually gives you the question. It gives you the assumption, so that it gives you the question that you have to answer with an assume. So in the first possible case is when you have actually an integral that doesn't make sense. So you must assume that the b is actually larger than -1. If that is not the case for all b smaller than -1, your integral, we say it's just 0, because your interval is either a point if it's -1 and the point has no area, or it is not well defined. So we actually have to assume, make that assumption. So if the b is less than -1, actually, okay, I'm sorry, I made a mistake. If the b is less than -1, then actually you flip the sign of the, so we can work with negative areas. So here you see the negative b less than -1. Yeah, and that's the first answer. Okay, so then there is the b larger than 0. That is a problem. Now, if you do that, if you assume that the b is larger than 0, what you then have is that you have the value that is infinity. So you have an improper integral for all the b's that are larger than 0. Also those, well, the second assumption is actually most critical. Okay, so that's the infinite value. Then you have the value where the b is less than 1, and then you have again the same expression as we had before. So you see that here we see that two cases that are distinct. So the case where b is less than -1, and the case where b is larger than -1 but less than 0, that they give the same formula. Okay, so then we are almost there. So we have the following cases, and then there are three cases we have examined. We have the improper integral when b is positive, and then we have the two cases that actually give us the same value. We do not lump these cases together because they are kind of separated, but this -1 and the 0. So if 0 is in there, we still have a divergent integral. Otherwise, when b is -1, we have 0 for the interval. And you can actually also see this, that this is covered by the special formulas, by the formulas we have here. Okay, So why do we write it like this? Because we have with the piecewise the either the open intervals or the closed intervals. So that's why here we have an open interval, we have a closed interval, an open interval, and then we have still two cases for the last case. So here is the solution then. So I said that this was a fused question. On the final exam, you would actually have a question that starts finally. It wouldn't start with finally, but where we have here you see a case analysis. Now define the function. And I do a reset here because I want to remove all the assumptions on the B. It's a function that is actually a piecewise function where the b is defined outside. So I could actually have used also here a proper function that either working with a lambda or with a sage-mod function. But the point of this question, so the point was twofold. So we had this case analysis with the assumptions on the bound of the integral to assist the integrator of Sage. And then we have the case analysis where you work with closed intervals where you have the square bracket or you have the round parentheses that give you the open intervals. Okay, so it's always good to check things. So here I check all cases for in the intervals to see whether it works. And I said that this is actually a function that takes in the b. So piecewise is a function of the argument. Okay, so question 3 is similar in nature, where we are looking at an integral, but the important variable is the upper limit. So we are defining the arc length, and the formula is given here. So for any function, it is the derivative of the square root of 1 plus the square root of 1 plus the square derivative. If you apply this to the arc length of the circle, and if the t is pi, so you know that the unit circle has area pi, we used this already, but the length of the circle, the circumference, is 2 times pi. So this is a test case that we are using here. And essentially this is also a test on numerical integration. So define a function arc length that gives you a 10-digit floating point approximation for any value of t. Okay, so how do we answer this? Well, we define the derivative, so we are working with the unit circle, and then we compute the integral for the special case. So this is the first part, compute the arc length of the first half of the unit circle. Okay, so the t is 1 there, so the integration interval goes from -1. -1 is fixed here, and the upper limit is 1. Okay, then the function that computes the numerical approximation is actually very simple. The whole equals true makes it go a little bit faster, so with that so there are two ways how to do this essentially. If you have the whole equals true, then what will happen is that and here in this case there is a symbolic antiderivative, that formula will be evaluated numerically. So in a way, if you like, it is a better way of working, but it's not quite general. Well, it is general for here for this particular case. But if you need only 10 decimal places, then you're much better off to work with the hold equals true, which does not use the symbolic representation. Okay, we're 25 minutes in. This is the calculus part. Let me now go while we continue with calculus. And also here, this is a very nice review question in the sense that it combines different things. So we have a recurrence relation for some numbers, and they can be defined by the Taylor expansion of a generating function. So you can define that function via the Taylor series on the generating function. So that's what the first part does. Then the second part is an exercise on memoization. So where you are asked to evaluate this two terms recursion but efficiently. So make sure that you can compute the 120th term. Okay, so we have the Taylor in SageMath. So here I illustrate how this goes. What is important here that you very well distinguish between the formal variable in the generating function, which is x, and then the term that is used in the Taylor series. So we can define the coefficient of the Taylor series. So this is then parameterized by the degree, the exponent of x. So the n that is used in the function t is what you pass as the end value when you get the coefficient of the Taylor expansion. So the Taylor expansion is computed rather fast here. But you could eventually also work with memoization and store all the previous and work with a generator if necessary. But that would be a SymPy question. So here you see the first 10 numbers. So you see these numbers actually grow rather fast. We will use these numbers to verify the correctness of the next question. So here you see I'm already scrolling through, perhaps a little bit too fast. But you see the solution with memoization, where there are several parts to it. And the parts that kind of missing is the two terms recursion. Here you see the two base cases for n equals 0, n equals 1, and then you see the general case. So this is the if-else. If-else is the control structure that you use to evaluate the recursion relation. So in a normal program, you would, instead of assigning to result, you would return. So the first mistake that some people already make here is to do the return. You cannot return, so you must assign to a result which you store into the dictionary, and then you can return the result. The other important aspect, and that's also what makes it efficient, is that if you have already computed your end coefficient, then it's in the dictionary and then you return. So dictionaries are efficient lookup structures. So the lookup will be most likely be logarithmic in the size of the data structure. So this will go very fast, and you see that we get the same sequence as before, and you will see that without any trouble we compute that huge number, the 120th term. Okay, so the next question is also memoization. It's a more complicated form of memoization, because it is a polynomial. And the polynomial has two parameters in there. So the Legendre polynomials, so the Legendre function that you write for this also has two parameters, and the dictionary in the memoization also has two parameters. So dictionaries can have tuples as keys. So we will store both the degree and the n. And then there is another issue that we have to normalize the expressions, or actually we have to store them in a canonical form. That's the other thing, because otherwise SageMath does not evaluate those expressions for fear of expression swell. Alright, so here is then where the definition goes. Again, in a way, it's not really pedagogically justified that I'm doing this so quick. I immediately show you the result. If you would code this up, you would, as we did in the lectures, there you see a much slower progression. We would first do this without memoization. And we would look at the Legendre polynomials and compare already against the Legendre p underscore p of SageMath to see that we are correct. So that's the preparation work. So then you, instead of returning, you assign to results, and before you return, you store in the dictionary. The dictionary which has this tuple index. So when you store also, you store with the entire tuple, both n and x. Okay, we verify first some base cases, and you see that the polynomial is expanded, stored in canonical form. Here we can compute, so this computation happens instantaneously. And the canonical form is useful in the comparison with SageMath. So the subtraction of the two forms will automatically lead to 0. Okay, so this is a very good illustration of a canonical form of a polynomial in one variable. Okay, so then we get at another very important problem, and that problem actually was answered quite well on the second midterm exam, and I showed this also how to do this in Julia again, so I can go extremely fast on this. This is a fused question. I'm on the review, I'm actually showing his to do in both ways. On the final exam, I may ask you only to do the slope of the tangent line, and that's it. How you do it, that's your choice. If you have to do it that way, then here you do it. It's just the tangent line, just the Taylor series truncated after the linear terms. So that's it, and in SageMath, this is the fastest way. So you can read off the slope immediately. Now this example is probably not too good because in the Taylor expansion you see too many ones. The last one is critical for the linear terms. The first one is the first coordinate of the point P, and the second one is the second coordinate of the point P. In somewhat longer way, so of course if I force you to do SymPy, SymPy has a series which is nice with a generator, but it asks you to iterate. It has no multivariate Taylor series. So then you might be better off with implicit differentiation. So here is the implicit differentiation where I declare a new function. I take the equation that I had for the curve and I substitute in y. So here I have declared y as a function of x. So it then suffices that I write capital Y everywhere. I don't need to repeat y of x. So that's important here. Okay, we get a symbolic formulation with the slope, and here I chose to do sequential substitution. So in the first part of the course, we dealt with expression simplification, and we made the distinction between sequential and simultaneous substitution. So if you do this with two subst commands, this is actually forcing a sequential substitution. If you do everything in one substitute, then you can do this with one dictionary. Now I'm realizing this could be the point where 9.6, the latest version of SageMath, complains because of the substitution here. It could be that you are forced to write x equals 1. It could be that that is necessary for you to do. Okay, fine. So I'm 35 minutes into this recording, and I'm now halfway, so I have 13 questions. We are getting into the last part. So the last part was not a question on the second midterm exam, but we practiced this before. So curves can be defined implicitly by equations, and that's, by the way, also the case with surfaces. And then in the rectangular coordinates, the origin might be a problem. Here you see that when you replace x by 0, y by 0, you actually get a 0. So 0 lies on the curve, but if we plot this, then you see I took 5,000 points, and you can kind of see that around the origin here, it looks like there is a gap. So this would be a nice continuous smooth curve, but there is a gap. And I'm not running this, but with plot points 5,000, there might already be a delay. Notice the syntax for implicit plot. We also have implicit plot 3D, but you will only do the 3D if you have an X, a Y, and a Z. Or, well, you can also plot cylinders, but 3D, you need to provide 3 tuples to define the range. Now, what's the point now of this whole exercise? Well, if we convert to polar coordinates, replace x and y by r times cosine t, y by r times sine t, then we can solve for r. And here you see the cosine square plus sine square getting in. And we know that this is 1, so you could manually substitute this, but you can ask Sage to do the trick, simplify, or you can do the full simplify. And this is one of these review problems where I still want to teach something here. You see that the expression has indeed simplified, but now we have the cosine in the denominator. And we have to decide on the range for t. So note that the cosine, which is also in the other curve, becomes 0 at multiples of pi over 2. So exclude pi over 2. And here I picked the range minus pi over 4, pi over 4. And you see that this is now in the default number of points. It is looking very good around the origin. However, the coordinate axis blocks the view a little bit. So here I have the axis turned off, and I put the 50 points instead of the default number of points. And now you see that 50 points for the upper part, 50 points of the lower part. With 100 points, I get a very nice plot, and that's much better than the 5,000. So that's 50 times better, simply because the r equals 0 was a singularity that got divided out. So here we do a geometric form of factorization. Okay, question 8. Question 8 is a question: if you solve problems, it may be beneficial to be be careful about what you're solving for. So this is an expression in two letters, x and a, but we once see this as a polynomial in x and once see this in a polynomial in a. So here I'm solving this with a solve. But you can also solve this via the reformatting. So another way of solving this using the technology that we have seen in the first part is to factor this. But um, group the coefficients along x or along a. So first we actually solve this for x, and then we find symbolic expression, because it's a quadratic form, but you have to observe that the a plus 1 is in the denominator. So this is a case where when we solve symbolically, it produces formulas that are not everywhere valid. So this is kind of the opposite what we did with the piecewise. We had a general formula, the integral with the upper limit, which we could write down everywhere but not evaluate everywhere. But with the piecewise we could do it anyway. Here we have the opposite. Here we have a formula where actually it's not really valid. So here also I could ask for a piecewise to define the solution of this quadratic equation in x. So what this question does, this question prepares for this. So you see that if we look at the leading coefficient, then the leading coefficient, which is in x squared, that coefficient actually has root a equals -1. So if you would rewrite the polynomial as a polynomial in x and factor the coefficients, which are then coefficients in a, then you would actually see the polynomials, the difficult spots. So here I'm solving this with the solve command. So this is another way of analyzing and looking at a polynomial, but now a polynomial in two variables. In the first part, we have seen how factorization is connected to root finding. Here we do the solving, and then actually we are rewriting this expression. So you see the a -1 is different, and also the a equals 3 is different. So then actually you have x can then be anything, because the polynomial collapses when a equals 3. Okay, so let's now go to another calculus problem. So here is the finding the point that is closest to the origin. So the constraint is actually the curve, and the target function is implicit. So the target function is given by x squared plus y squared, and that's an expression that we have seen a lot with the circle. If you put x squared plus y squared minus 1, you have all points that are at distance 1 from 0. Here we are trying to minimize the square of the distance of the point of any points xy. It's a point xy that lies on the curve, so defined by that constraint. So here I'm defining the constraints as functions, because then I get the gradients with one instruction. The gradients that are used in the setup of the system that must be solved, the last equation is always the constraint. So I'm interested in the distance that is closest. So I'm going to solve this, and I'm going to look at the solutions, selecting the solutions. That's why I put dictionary equals true. That makes it easy to select the coordinates. Now the lambdas appear sometimes with complex values, and they are of course not interesting. We have two real solutions and we evaluate the target. You see that the last value is closest to the origin. So the solution, the answer to this problem is that the last point, and you can read off the coordinates there, lies on the curve and it lies closest to the origin. If you like, you can make a picture of the curve and then also put the point on that curve. So that would be the review question visualized, the answer to the review question visualized. Okay. Here we have the solution of polynomial systems again, and this could be an alternative to the solve where I'm using the QQ bar. So the QQ bar is symbolic numeric solving. If I define my polynomials over the QQ bar and I ask for the variety of the ideal defined by the two polynomials, then I actually get very nicely the intervals out there. So here you see the four solutions of these two quadratic equations. And they are given in the interval representation. So this makes the connection with the symbolic numeric factorizations. So with the lexicographical term order, the polynomial system was reduced to triangular form, and the polynomials were in that triangular form solved via symbolic numeric factorization, which is equivalent to stating that the root finding was done with complex intervals. There are also other ways to do this. What I haven't done here is via resultants, so that would be an equally good way. You could work with the explicit Gröbner basis and then also solve. So here you see the two real solutions. This gives you the coordinates of one of the real solutions. So this gives you the y coordinates. I'm a little bit running over time, so I don't want to stretch this review any longer than necessary. Here you see the solving of a differential equation, where also here this is a two-part, so there will be multiple parts of this. So I could take the same differential equation and ask one version, give the exact solution, then on the other question ask for a numerical solution, numerical method, and then I can also ask for the Laplace transforms of this differential equation. So there are many ways to solve the same problem. We teach all many ways because in the hope that you will remember when you need one, you remember at least one of the solvers. Here you see that SageMath can solve this problem symbolically with the initial conditions, the two initial conditions. This problem has a unique solution, and you see here it is a periodic, but there is a exploding amplitude. So this solution actually spins out of control. That implies that in a numerical solver we will be careful about the range. So here we rewrite this problem as a system of two first-order differential equations. I'm using ODE int, so there are other solvers that we can use. So I'm not sure if we have used ODE int in the lectures. SciPy may have other ones. So what is important here is that you have to define a range. So we are starting from the pi over 2 to 2. That's the interval, and I'm using 100 points, and then we get the last value there. And we can compare with the function that we defined from the symbolic solution. Okay, I have too many problems prepared, or I spent too much time on the earlier problems. With linear algebra, we can define most matrices are structured matrices, so we have a formula for this. Here I'm solving this in two stages. We have the indexes, so you can see that this is linking back to the variables in the first question. So I have a sequence of variables in the tuplets, and here I'm solving this first with the indices. So so I'm now actually giving it pedagogically justified. How could you approach this problem? It's going to be a very hard problem if you do this right away, because if you make a mistake with the indexing, you will get an error. Here, the index, you have to see that all these numbers here are lying between 0 and 8 included. So you can use these numbers then in the indexing. And by the way, this is another nice use of the conditional expression. Of course, it is good if you forgot conditional expressions, you can use a regular Python function with an if-else. But the point is that we can define matrices via formulas. So here is how one defines a symbolic doublets matrix. The last question is essentially a setup question. We have a linear programming problem. It is a maximization problem. So if we set it up, we have to define it as a maximization problem. All the variables are non-negative, and we have constraints that are less than or equal. And this is the max equation here. So we first show the problem. That is more than half of the problem done, because then SageMath takes over for us and it gives us the optimal value and the location where the optimum occurs. Okay, I know this went way too fast. On the exam, you will not get that many problems. See, here I tried in less than 50 minutes to get through so many problems. You will have on average about 10 minutes per question. Okay, so I thank you for watching. So this was the last recording in this course, and I hope that these recordings have been beneficial for you.